So what I'm going to do today is give a quick overview of the approach that we had, which was to take the Learning to Prune framework and apply it to these E-VRP problem instances. And this was done by me with my supervisors, Deepak Ajwani and Paula Carroll. So I'll just the basic overview of the main details, and then we can get into the meat, I think, afterwards, if we want to discuss that. Okay, so the slide should change. Okay, so the first thing I'm going to do is give a very quick overview of what the Learning to Prune framework even is. So basically, it's another one of those machine learning based frameworks that you might not have heard of, but it's very, very simple to describe. Effectively, the main idea is that we want to take a difficult combinatorial optimization problem and reduce the search space for it by fixing a large number of the variables. Now, I have written here that we fix the binary variables, but actually we can apply this equally to integer variables in another problem, or even continuous variables. And the idea that is, if we fix a large number of these variables, hopefully we make it easier to solve. And this is similar to the assumptions we make in column generation approaches, where we know that in many problem instances, when we actually get a solution, a large number of the variables will be non-zero. So we really don't need to worry about a large number of those variables or columns to begin with. So we see this kind of picture a lot in machine learning circles. We don't really describe it or deal with it too much apart from the bottom part, which is when we're talking about optimization problems, we mainly deal with our constraints and our variables. And even in binary integer programs, we have a lot of variables, and even if their domain isn't particularly large, so they can just take two values, if we have enough of them, we have a very difficult problem to solve because we have an extremely large search space. So in many cases, we just don't have good pruning techniques for dealing with these kind of problems, especially for newer problems or ones that aren't researched that well. We don't have these algorithms or heuristics, so our approach is to try and train a classifier to do this work for us. So we hopefully can predict a large number of these variables that can be fixed. And instead of having the original problem, we have something that looks a bit more like this, where we have a large number of these variables set to a specific value. In binary integer programming case, we might set them to 0. And then we deal with the rest later on by sending the reduced problem to a MILP solver. So this is effectively a math heuristic. And we have good reasons to think that this can be applied successfully to the E-VRP because we've done it with other problems before, and lots of other people have as well. Some of those examples are the maximum clique enumeration problem. We have the facility location problem and k-median problems, traveling salesman problem, which I've worked on myself, and CVRPs as well, among others. So I'm going to go quickly through the TSP because that's what I worked on already, and it gives kind of a nice jumping off point to talk about how we're going to use this approach for solving the E-VRP. So the basic idea that we're probably all familiar with is that when we're solving a TSP and we want to solve it as an integer program, we'll write down a formulation in which all of the edges of the underlying graph are associated to some binary variable. And when we take those binary variables, what we want to do is find some assortment of values for them that give us a nice feasible solution, where the ones that are active are part of our solution and the ones that aren't are not part of our solution. So in the Learning to Prune framework, what we want to do is take this underlying graph and learn about which of those edges we can essentially remove from consideration, or which of the associated variables we can fix to 0. So we'll have a classifier take our graph, which was complete, and reduce it to something that looks maybe like this. What's left over, hopefully, is something that we can deal with a little bit more easily. So the way we do that right now is to take a data set of existing problem instances that we can solve to optimality. And we say we have two classes that we want to worry about. The set of edges that we think are unlikely to belong to an optimal solution, and a set of edges that we think might be more likely to belong to an optimal solution. And the hope is that the set of edges that we think are unlikely to belong to that optimal solution is very small. So we want to do this with a classifier that uses features for these edges that are expressive, yes, but also relatively cheap to compute. So those features might include things like statistical features over the edge weights. So for example, we might compare the weight of one edge with those of the others in its locality or with the entire graph. And that might give us a picture of how important that edge is. We might explore the branch and bound tree, or just take the linear relaxation of the original problem and see what that can tell us. Or we might do some exploration with some graph algorithm, some features derived from graph algorithms. So in practice, what we can do is reduce the number of edges in a TSP by a large fraction. And what that does then is actually help us to solve them much more quickly. So when we write down a formulation that doesn't have any of the fancy bells and whistles that Concord has, for example, we can reduce solve times quite significantly. And that gives us hope that when we apply these to different kinds of problems, that we can achieve the same kind of results where we don't have known effective cuts, for example, that are specifically effective for some problems. But we have to be careful when we do this. We need to make sure that whenever we reduce a problem instance, that While reduced, it's still going to admit a feasible solution. So one way to do that is just to insert a known solution in there. And if we have an approximation algorithm that can give us an approximation guarantee, that's also good because we can guarantee feasibility. And we can also guarantee the worst case performance, even though we notice that in general, even if we remove some of the optimal edges, as long as we have this feasibility guarantee, we can still get quite close to optimal solutions for the TSP. So this generally means within 1% of the optimal solution. So that's also quite encouraging. And then the whole point of this implementation was to see if we could extend this to much more challenging types of problems. So this is one of the reasons why we picked the E-VRP to work with. So the E-VRP is fairly straightforward from the sense that it's pretty much what's in the name, but I'll do a little bit of an introduction of it first, just to describe what it's all about. So basically it's the same as our other CVRPs, except now we have to worry about the fact that our vehicles are electric vehicles, so they're going to run out of battery at some point, but we still want to service our set of customers and we still want to minimize some objective. In this case, it's the routing time. And this is the time in which we have allocated for traveling, for charging our vehicle at a charging station, for which we have detoured to that charging station and for which we service the customers as well. So those routes have time limits, so we don't want to exceed them, and we want to prevent the vehicles from becoming stranded, as I said. So the extra difficulty here is that the charging actually may be partial, so we don't just decide which station we want to go to. When we get to that station, we decide, okay, how long am I going to charge my vehicle for? And to complicate this a little bit even further, these charging functions are non-linear in the state of charge of the battery when it arrives at that station. So we have, like we have here on the bottom right, that describes the state of charge of the battery and how long it will take us to charge it. We can take a piecewise linear approximation and still make this a mixed interlinear program, but at the same time, this introduces a lot of extra variables, continuous and otherwise, to our formulations, which make it even more difficult to solve. So in general, we have lots of nice existing formulations for these problems, but at least from the point of view of some other nicer problems that we can work with, we have relatively weak LP relations, which just basically means that trying to solve these to optimality is probably a lost cause in the case of the larger problem instances. So made worse, or making this worse, is the fact that in some of these formulations, and in particular the one that we choose to implement our framework with, we need to duplicate some of these stations and hence duplicate the variables because we might need to make multiple visits to these stations as well. And then worse is that these convex functions that describe the charging at a state of charge and how long it takes. So solving even very small problems is difficult. And that makes obtaining labels for our training data quite difficult. However, we do have some encouraging ideas about why this might be useful in particular, because when we take this kind of formulation, we can look at it and see that there are two types of variables that are continuous, but we can directly tie them to the values of our edge variables. So that is, if our variable xij is 0 because we set it to 0, because that's what our pruning algorithm or our pruning heuristic that we trained told us to do, then we can also say that the state of charge variable is also going to be 0, so we don't need to worry about that either. And we don't need to worry about the time at which we travel along this edge either. So we get 3 times the level of sparsification that we get, or that we would have gotten otherwise. And this is, just to mention, is the arc-based formulation from Aurélien Foyer's nice paper about improved formulations for this E-VRP. So the question now is, can we just take our Learn to Prune framework and apply it directly to the E-VRP? And the answer is no, not really, because now we have a large to worry about, which we didn't before with the TSP, or even really with the CVRP. So on top of that, what we notice is that when we're removing these edges, while it wasn't really that much of a concern how we did it for the TSP, when we try and do this for the E-VRP, removing them incorrectly, or so misclassifying the edges as not belonging to the optimal set, might have absolutely catastrophic results in our performance. So we need to be careful about how we do that. And because we can only solve really small problems to optimality, that means that we have to solve lots of extra problem instances to get more labels, because we still need to have lots of labels to train with. And that means that when we solve a small problem, we get a commensurately smaller number of labels and samples to work with. And on top of that, because we have a heterogeneous set, it turns out that the edge types that we work with, some of which are more important than others, we don't have that many labels for. So for example, there are lots of customer to customer edges in these graphs, particularly the smaller ones, but there might not be many customers to station edges or station to customer. The direction here is important as well, or station to depot and so on. So it turns out that really we only have enough samples to train on the customer-to-customer edges. So that's the most common set. And maybe we can just train on those and just prune those, and maybe that's enough. So maybe if we just remove a large fraction of the customer-to-customer edges, that might be enough to do well in terms of reducing the solve times. It turns out that that might be the case for the small problems, but it's not the case for the larger problems. And really, it's the larger problems that we want to worry about. So the way we deal with that is we look at these other edges and find another way of getting some information about them. And to do that, we rely on the ability for us to solve these problems to some extent quickly. So we look at existing heuristics that solve these problems quickly. They don't have to solve them particularly well, but they just have to give us a feasible solution. And what these feasible solutions give us is an idea of how often these edges that we have in the underlying graphs actually belong to any good solutions. And if they belong to, or if a given edge frequently appears in good solutions or any solutions at all, then it's more likely to be in a set of edges that we should not get rid of. And if it doesn't appear that often, then maybe we should get rid of it, and maybe it's not that really necessary to use. So I'm aware that I'm running out of time already, so I'm going to skip past the detail, but basically we make use of one of the first heuristics proposed to construct solutions for the E-VRP with nonlinear charging function based on effectively looking at the TSP, solving that for a given problem over the customer nodes, then constructing time feasible routes which don't consider the energy, and then using those energy feasible routes, or sorry, using those time feasible routes to construct energy feasible routes by solving a fixed route vehicle charging problem. And I'm going to thank Nick and Jorge as well for making their implementation of this heuristic for solving the fixed route vehicle charging problem on GitHub for Python implementations. That was quite nice. But effectively what we do is we construct lots of solutions and we look at the frequency that these edges appear in them, and if they appear often, then they're good edges. So what we can do is combine this information, what we get from our machine learning based classifier, and use that to remove a large fraction of the edges. And now we can tackle large problem instances. But we still have one major issue, and that's if we miss absolutely terrible damage to the performance that we have. So we attempt to undo this to some extent by making this not just a static process. So we don't just prune once, we repeatedly prune variables and then maybe release them if we have a reason to do so, or at least to have some indication that it might be a good idea to do that. So this is based on a Fix-and-Optimise heuristic. So effectively what we look at is some signal that tells us that these variables might be good to reintroduce to our problem every time we solve one using MILP solver. And what we take here are the reduced costs. So if they're negative enough, then maybe it might be a good idea to reduce or to release those variables for optimization if we want to solve them or solve a new problem in the next iteration. So it's not static. It's, again, an iterative process, and that helps us to escape particularly poorly pruned problems. Basically, we just do this repeatedly, making sure we guarantee feasibility at all times by maintaining the best solution inside of our set of edges that we consider for optimization. And at the end of some fixed time, or within when we reach some stopping criteria, we just exit with the best solution that we found. Now, one other thing that we need to worry about, because we've chosen to use a formulation that requires station duplicates, is how do we pick how many stations we should use? So we could try to optimize over the stations and the edges that we're using simultaneously, but that causes all sorts of complications. So what we attempted to do was to actually have another separate machine learning based classifier, or rather regressor, determine the number of edges or number of station duplicates that we should have. But this turns out to be quite difficult to do. So we have a heuristic instead that generally does quite well. And this is basically to just look at the frequency with those stations appeared in good solutions as well in the solutions that we sampled. And if they appear more often, then it's more likely that we're going to need to use multiple copies of a given station. So we use that basis to if necessary for specific stations, but not all of them. So we don't make this a uniform set of copies. And just from observations with the smaller instances, when we attempt to solve them to optimality without any reduction of the problem, we notice that when we have up to 10 customers, we can obtain optimal solutions in 18 out of 20 of the cases, and when we use these estimates for the duplication. And with the other two instances, we can get quite close to the optimal solutions as well. And one thing that we have to make sure that we do as well is to, when we solve these reduced MILPs repeatedly, what we're going to focus on is very, very short runs, because we want to take advantage of the strong heuristics that we're using very early on in the branch and bound tree. And on top of that, we don't want to spend a long time solving them, because what we've noticed as well is that when we're solving these kind of optimization problems with MILP solvers, we can get good solutions quickly, but we might spend 99% of the time plus trying to certify that that's a good solution, or that's even an optimal solution. So it's not necessarily a good idea to spend too much time trying to solve these directly as a MILP problem. So we might abort early. So that's where the Redoute idea comes from. We reduce the problem and then route. And this requires us to have this large data set of problem instances, which we generated to help us do that. 450 problems for, which is still a relatively small number, but we generated that number for training, and then we had another 350 or so for testing our classifier to make sure that it did a good job at customer-to-customer edge classification. So the basic framework looks something like this. I'll go through it very quickly. Essentially, we have a problem instance. We have a trained classifier for our customer-to-customer edges. It's going to take that problem instance and give us scores for each of those customer-to-customer edges and say what's the likelihood that we should keep it. And also with our heuristic that we have based off the construction heuristic from the original proponents of the E-VRP, we get our edge statistics. So we see how likely those edges in the graph belong to optimal solutions, or sorry, good solutions, not necessarily optimal. And then we also get the best solution from there and keep it. And we want to feed them into our MILP solver. So we construct a problem, and based on what we get from our edge statistics and our customer-to-customer classification, we reduce the MILP heavily, basically reducing the number of edges to a very, very small fraction of those that we could possibly have. And we ensure that the best solution can still be found inside that reduced problem. And then we solve this in an iterative process. So these purple boxes are supposed to represent static operations, so these never change, these inputs, but these in the red boxes are things that will be continuously updated until we reach some stopping criterion, and we output the best solution then, using the best solution that we found with the MILP solver to continuously update the edges that are being involved to maintain feasibility, and also using the reduced cost to help us have a signal about which variables we should be removing or accepting again into our next reduction problem. So as was said, is this going to get us optimal solutions or better than the best known solutions? No, not quite. But we have some encouraging performance that shows that although we have quite a good bit of success for these problems on for this framework on relatively less challenging problems, we within the time constraints that we had can do fairly well at the start anyway, and we continue to we are intending to continue developing this. So basically what we could do was assign 1 hour of time for our solver to actually solve each of these problems. So by that I mean this does not include the time that was required for training the classifier. It's just the time that we take to classify the edges with the classifier, to do the sampling with our initial heuristics, and then to do the iterative process of creating MILPs and then solving them. Obviously, not all the problems took that long. So for some of the smaller problems, we would abort depending on the size of the problem. If after a certain number of iterations we had no improvements, in general, what we could see was that for the smaller problem instances, we might get near to optimal or even the optimal solutions. This performance obviously degrades, as you can see on the right-hand side, as the size of the problem increases. So we're not quite at the level of success that we see for some of the less involved problems like the TSP or their family. And it seems that without a more comprehensive pruning heuristic, and by comprehensive I mean one that can accept or classify more edges than just customer-to-customer edges, we think it's probably going to be difficult to make much more progress for the larger problem instances. But that's not to say that we can't do that. And interestingly though, the performance actually didn't continue decreasing. It increased for the largest set of problems, which is strange, but it's probably down to the fact that in these problem instances, they're all set within the same area, and the larger the number of customers, the smaller the edges. So it's more likely that if we misclassify some of the smaller edges, that it'll do less damage to our performance. So on top of that, one thing that continues to be a common theme throughout these is that if we want to train classifiers to do this kind of thing, we notice that actually when we solve the most difficult problems, they're the ones that we want to use for a training set. So when we select the training set, we want to use the ones that were the most difficult or took the longest time to solve to optimality, because they tend to give us better generalization to larger problem sizes. Okay, So I'll just skip through this because some of it's basically just down to implementation details as well. So we also had issues with trying to implement this. There was a bug with the Express solver that we're using, which is quite a nice solver, but it's not just the Python wrapper we're using. It appears to be just an issue with Express, where when we're trying to fix and release lots of variables, it does not like continuing to solve problems in that manner. It sometimes is not like accepting warm start solutions, which is pretty important for us because we don't want to repeat the effort every time we attempt to resolve a problem. So what will happen a lot of the time is Express will simply reject the from a previous iteration, meaning that we have to start from scratch in terms of optimization, or we have, but for some reason, and we can't control this, use an optimization heuristic on the solution that we provided, making it much worse, and then basically degrading the performance again to the point where it basically just nullifies any progress we've made. So it's very difficult to have this work in that case for all these different problems. So we could actually get much better performance if we sat down and tailored our our heuristic to each individual problem, but obviously that's not a feasible thing to do. So once we fix those, we expect the performance to increase, to improve rather, and running times to increase quite significantly, to decrease quite significantly. And there are other things we need to consider about making the implementations a bit more efficient. But the main thing we think that is most promising to work on is helping us sample these solutions more quickly. So for a couple of reasons, we think that being able to sample lots of feasible solutions, whether they're good or not, so they just have to be okay, can help us. One of those is because the more solutions we get, the better our statistics will be for looking at our edges and helping us determine whether or not they should be candidates for good solutions, for optimal solutions rather. And there are lots of ways that we could do that, but the approach we've taken was to adapt these machine learning based end-to-end heuristics to help us do that. So before we do the pruning at all, we have another heuristic based on machine learning methods that just gives us a solution directly, or hopefully many solutions. And basically it's the same concept as the one that Wouter presented a couple of years ago. And once you deal with managing to ensure feasibility at all times, actually this can work quite well, and we're getting quite a lot. Hopefully we can improve the results that we have from our Redoute solver as well by including that. And the other reason why that might be particularly effective is because what we can do is use these to act as, instead of categorical labels, but maybe continuous labels. So maybe we don't need to obtain optimal solutions to use as labels, maybe we just need to labels for our classification tasks instead. And then once we have all that together, perhaps we can use this approach to solve E-VRP problems with different formulations. For example, one that's based on recharge paths, also in that nice paper by Aurélien Fauger and Jorge. If we can remove any of the edges, then any of the paths that include those edges can go as well. So remove paths. We can also use machine learning based heuristics to help us consideration. So in that direction, we think we'll see a good bit of progress. But for now, that's everything, and thank you.
Thank you very much, James. That was a really, really nice presentation. Thank you very much for that. Do we have any questions from the audience?
Hi, yes, I have a question.
Yes.
Hi, James. Thank you for your talk. I wanted to know if you are comparing your machine learning classifier learning to a baseline to know if it is actually learning important information.
By that you mean if our classifier is actually performing well or not?
Yes.
Sorry, the audio cut out there. The metric we use to determine the quality of the classifier is the false negative rate and the true positive rate. That is the biggest indicator of how well we do. So pruning if we don't have a relatively low false negative rate. And by relatively low, I mean false negative rates lower than 10%, which is actually extremely high. But really, we want to have false negative rates lower than 5% for the optimal edges. If the classifier gives us anything less than that, then it tends to not perform particularly well. But we have the constraint that we need to use relatively simple classifiers, because when we get to large problems, we have to make hundreds of thousands of predictions for these edges. So the real challenge is to get it to work for models like linear regression models, which at times, or linear support vector machines, which we can just about get to. But the real problem is coming up with enough samples to actually get us to a point where our classifier can learn to distinguish the edges properly. I hope that answers the question.
Yeah, thank you.